Right now, deep beneath the summit of one of the most active volcanoes on the planet, magma is building pressure. Tiltmeters are bending, the ground is swelling, and scientists at the Hawaiian Volcano Observatory are watching a very familiar set of numbers creep toward a threshold they know all too well. Kilauea volcano is reloading. The most recent eruption episode, Episode 50, ended on June 27, 2026, after producing lava fountains reaching 700 to 1,000 feet into the Hawaiian sky. And based on every instrument USGS scientists have at their disposal, from seismometers to gas sensors to precision tiltmeters, Episode 51 is imminent. The Hawaiian Volcano Observatory has forecast its onset between July 11th and July 13th, 2026. So today, we are going deep. We are going to look at every piece of monitoring data currently coming out of Kilauea's summit, the seismic signals, the tiltmeter curves, the sulfur dioxide plumes. And then we are going to put all of it into the context of Kilauea's geologic record to ask the question that matters most. Is this cycle escalating? And where does it end? Stay with us. This one gets fascinating. To understand what Episode 51 is, you need to understand the eruption cycle that spawned it. On December 23, 2024, Kilauea's summit caldera, Halemaumau crater, erupted. But this was not the kind of eruption that simply runs and runs. Instead, it established a pattern of short, violent lava fountaining events, each lasting just hours, separated by pauses that can stretch from a few hours to several weeks. As of today, the volcano has completed 50 of these discrete episodes, 50 individual bursts of magmatic violence, each one a complete pressurization and rupture cycle of Kilauea's shallow summit magma reservoir. Episode 50, the most recent one, is our best benchmark for what 51 will look like. It began on June 22, 2026, and lasted approximately 7 hours. During that 7-hour window, fountains from the primary north vent inside Halemaumau reached heights of 700 to 1,000 feet. That is 200 to 300 meters. The peak lava effusion rate hit approximately 330 cubic meters per second. Lava flows blanketed more than 50% of the crater floor, adding yet another layer to the accumulating volcanic pile steadily filling this ancient caldera. Then it stopped. The pressure discharged, the fountains collapsed, and the volcano entered its current inter-episode pause. But it is not dormant. Far from it. Every instrument monitoring this volcano is telling the same story. The recharge is nearly complete. Let's start with seismicity, because the earthquake record is one of the first things scientists look at when assessing what a volcano is about to do. Right now, seismic activity at Kilauea's summit is low, and that is actually expected and scientifically meaningful. During inter-episode pauses, you typically see a suppression of the larger earthquakes that accompany fluid movement. What remains is a persistent, low-level tremor signal beneath the caldera. But here's the detail that matters. Embedded within that tremor are periodic bursts. HVO scientists interpret those bursts as gas piston cycles, a rhythmic rising and falling of the magma column within the eruptive vent, driven by the accumulation and release of volcanic gases. Think of it like a pressure relief valve cycling open and closed repeatedly. Every time that gas piston fires, it is a reminder that the magma column inside Halemaumau is sitting very close to the surface. Now, critically, there are no earthquake swarms along the East Rift Zone or the Southwest Rift Zone. No tremor migration outward. No elevated seismicity along the rift arms at all. This is very important. Seismic migration into the rift zones is one of the clearest precursors to a potential flank eruption, the kind that brought Kilauea International headlines in 2018. The absence of that signal means magma is not currently forcing its way into the rift system. The volcano's attention is firmly concentrated at its summit. That is the current situation: confined, pressurizing, and recharging. If seismicity tells us where the magma is moving, tiltmeter data tells us how much. And the tiltmeter story coming out of Kilauea's summit right now is one of the most precise volcano forecasting tools we have ever developed. Tiltmeters measure ground deformation at the sub-microradian scale. During an eruption episode, magma evacuates the shallow reservoir and the ground deflates. The tiltmeter curves plunge sharply. During inter-episode pauses, magma recharges the reservoir from the deeper supply system, and the ground inflates. The tiltmeter curves trend steadily upward. Plot episode after episode together, and you get a perfect sawtooth wave. Eruption. Deflation. Pause. Inflation. Eruption again. Since episode 50 ended on June 27th, the Wekahuna Tiltmeter Station, sitting on the northwest rim of Kilauea's caldera, has recorded approximately 14.1 microradians of inflationary tilt. Here is why that number is significant. Episode 50 itself produced 15.3 microradians of rapid deflation as the pressure discharged. That means the system has already recovered about 92% of the pressure it expelled during episode 50. The system is not approaching critical pressure. It is essentially at critical pressure. Geoscientists did note that the inflationary trend was briefly interrupted by intermittent deflationary shifts on July 9th, small pauses in the recharge rate that temporarily delayed the forecast onset window. But the inflation resumed. This kind of jitter in the tilt signal reflects just how dynamic and sensitive the shallow magmatic plumbing of Kilauea really is. The system does not reload like a simple cylinder. It breathes. It pulses. And right now, it is nearly full. Gas emissions are the third critical monitoring parameter, and they tell us something that seismometers and tiltmeters cannot: what the magma itself is doing at a chemical level. The primary gas of concern at Kilauea is sulfur dioxide, or SO2. Sulfur dioxide is released when magma that is supersaturated with dissolved sulfur ascends to shallow depths and experiences pressure reduction. It is essentially a measure of how much fresh, hot, volatile-rich magma is sitting at shallow depth. During the current inter-episode pause, sulfur dioxide emission rates from the summit are estimated between 1,000 and 5,000 tons per day. Let that sink in. Even at the lower bound, 1,000 tons per day. That is an enormous amount of volcanic sulfur pouring into the atmosphere during the pause. For comparison, Kilauea's background emission rate between eruption cycles is typically on the order of a few hundred tons per day. The current inter-episode rates are running 2 to 10 times that background rate. This tells scientists something unambiguous. A shallow body of magma is still present beneath Halema Uma'u, still degassing, still releasing volatiles, and still capable of driving another episode. These elevated gas levels are also producing significant volcanic smog, or VOG, that is being carried downwind across the Hawaiian Islands, affecting air quality in communities across the Big Island and beyond. Gas emissions from the East Rift Zone remain below detection limits, consistent with the absence of seismic or deformation signals there. All the volcanic energy is concentrated at the summit. Now let's zoom out. Because Kilauea's current behavior does not exist in a vacuum, this volcano has been erupting episodically for centuries, and the geologic record gives us crucial context for interpreting what we are seeing today. The closest historical analog to the current sequence is the early phase of the famous Hu'u'o'o eruption, which began in January 1983 on Kilauea's East Rift Zone. During its first 3 years, episodes 4 through 47, spanning 1983 to 1986, Pu'u'o'o erupted in a remarkably regular episodic pattern with an average recurrence interval of 26.5 days between fountaining events. That regularity was driven by a consistent magma supply rate coupled with a stable confining structure at the vent. Eventually, that structure changed, the episode stopped, and the eruption transitioned to the 35 years of near-continuous lava flow activity that would reshape the lower flanks of Kilauea entirely. Going back further, the Mauna Ulu eruption of 1969 to 1974 began its first 7 months with 12 distinct fountaining episodes, fountain heights reaching up to 540 meters, before it also transitioned to a more continuous shield building phase. Then there is 2018. The catastrophic drainage of Kilauea's summit reservoir fed a massive fissure eruption on the lower east rift zone that was the largest in more than 200 years, demolishing entire neighborhoods. That was a singular catastrophic failure of the system, not episodic, but a complete structural collapse. The current 2024 to 2026 sequence is different from all of these. Its episodes are shorter, more erratic in their recurrence intervals, and confined entirely to the summit caldera. The recurrence has ranged from as little as 16 hours between early episodes to more than 2 weeks between later ones. This variability suggests a magmatic system in a state of dynamic instability, not yet settled into a Pu'u'o'o-style regularity, not heading toward a 2018-style collapse, but something in between, still finding its equilibrium. So, Episode 51 is coming. The tiltmeters say so, the gas data says so, the seismic tremor patterns say so, and the Hawaiian Volcano Observatory's own forecast window of July 11th through July 13th, 2026 says so. What should we expect? Based on the trajectory of this eruptive sequence, Episode 51 will likely begin with a rapid seconds to minutes switch from inflationary to deflationary tilt, a signal any trained volcanologist reading the live data stream will instantly recognize. Lava fountains will emerge from one or both of the primary vents inside Halemaumau, almost certainly reaching several hundred meters. The episode will last somewhere between 4 and 12 hours, consistent with the statistical spread of previous episodes in this sequence. And then it will end, the system will deflate, and the whole recharge cycle begins again. But here is the larger question that the scientific community is watching very carefully. Will this eruptive sequence persist, escalate, or transition? As long as Kilauea's magma supply continues at its current rate, which shows no signs of declining, the episodic cycle is expected to continue indefinitely. But volcanologists are monitoring for any signals that could indicate a shift, a transition to continuous eruption, like Pu'u'o'o eventually did. Evidence of magma propagating into the rift zones, which would fundamentally change the hazard picture. Or even a return to a quiescent period, a complete shutdown of the shallow system. None of those transition signals are present today. The hazards remain confined to the closed summit area of Hawaiian Volcanoes National Park. Volcanic gas and airborne tephra, including Pele's hair, those delicate strands of volcanic glass spun from erupting lava, are the primary concerns for surrounding communities downwind. Kilauea is performing exactly as its geologic history predicts it should. It is a volcano in a state of perpetual, restless activity, cycling through episodes of explosive beauty and geological consequence. Episode 51 is the next chapter in a story that began millions of years ago on the floor of the Pacific Ocean, and scientists will be watching every second of it. If you want to watch the live monitoring data for yourself, USGS Hawaiian Volcano Observatory publishes real-time updates, webcam feeds, and tiltmeter graphs at volcanoes.usgs.gov. The data is public. The story is unfolding in real time. If this video helped you understand what is happening beneath that Hawaiian summit right now, hit the like button, subscribe if you haven't already, and drop a comment telling us what you want us to cover next. This is Geohazards Explained, and we'll see you for episode 51.